Welcome guys, so today we will be doing part 2 of GPT from a beginner's perspective, specifically nanoGPT, which is a beginner-friendly code base for understanding generative pre-trained transformers. For those of you who haven't seen part 1, you can check on my YouTube channel, it's there. And also for my Chinese viewers on my WeChat channel, you can also find it there. So basically what I did in the part 1 was just explaining the code base from a beginner's perspective, going through each code line and sharing my understanding of it. So the last time we stopped at self-attention, and today we will be going into detail about what it means and how the standard transformer architecture compares with that of Karpathy's nanoGPT transformer. So we will be going into detail. This is the most important part of the whole understanding of GPT, which is the self-attention mechanism that was applied into the transformer in order to make it predict the next token more accurately. So one big difference between the standard transformer architecture and that of Karpathy's nanoGPT is that it doesn't have an encoder, so he only implemented a decoder-only transformer. So, and it doesn't have this cross attention. So as you can see from the standard transformer, we have an encoder and then a decoder layer. So the encoder meets up with decoder through a method called cross attention, and that's how it was able to feed in its output into the decoder part. So why was this made in the standard paper? It's because the transformer was presumably built for translation. And so what it does, it translates one language into another. So there was a need for encoding one language and then passing that output onto the decoding layer. But for nanoGPT, it's a character level transformer. So which means there's no need for encoder. So we only need a decoding layer because we just want to predict the next character in this case. So today we will be going through the key parts of this operation, which is attention. So basically attention is a communication mechanism. So you can think of it as sort of nodes in a directed graph, and these nodes are aligned in such a way that each node is kind of the aggregated sum of other nodes. It could be the preceding nodes, or it could be the next the previous nodes, sorry. So for the nanoGPT code base, it only has a decoder, so which means the attention here is only decoder only. So nanoGPT is a decoder only self-attention, which means the nodes are aligned in such a way that they only predict the tokens are aligned in such a way that they only talk to the previous tokens, and they will not have to communicate with the next tokens or the next character, because that's what we are trying to predict. So this is very interesting, and some of the important key points to note here is that one key feature of the attention in general, it has no notion of space, which means each node doesn't necessarily know where it is. So that's why an encoding is done in order to provide more information for each node. And another is that it's data dependent. So for each node, which is kind of the weighted sum, so that sum depends on the data of that node and its preceding nodes or its preceding stages. Yeah. So there's a trick that was applied in the attention mechanism, which kind of goes into mathematics. And so what Karpathy did is took us through the basic understanding of matrix multiplication, and then he showed us some examples on how this trick was applied into the transformer attention layer itself. So what is this mathematical trick and how is it applied in the self-attention layer? So first of all, he took us through some examples. So the main goal here is how do we get the tokens to talk to each other? And since we are developing a decoder-only transformer, we would like the tokens to talk to each other in a certain way. So in this case, what he was doing is the best way to get the tokens to be able to predict the next token is to actually have them only communicate to their preceding tokens. So in version 1 of how we get the tokens to talk to each other, so here he basically created a bag of words that is a container to hold our matrices. So a bag of words or tensor of B by T by C, batch, time, and channels. And so we are looping through each batch, and inside each batch, we are going through also the time of that batch. And then at each time, we are trying to get the preceding values at for that particular token. And then we print the output, which will be the average of those preceding values, as you can see here. So when we do that, for example, if we print the input here, which is, let's say that we print the 0th values of x, and then what we get here is just simply this matrix. Now, what will be the output for this matrix? So what we want is the output to be what? The average sum of the preceding tokens. For example, here we have, you can see the first value here is the same as the first value here. But when you come to the second value here, it will be the average of these two values, or these two rows. And the same goes for the third one. It will be the average of these 3 rows, and so on. So this is actually a basic level of how the tokens can communicate with each other. But it's not very efficient. So what he did is he took us through matrix multiplication, because that's how we can efficiently get the tokens to talk to each other. So in his example, let's say, for example, here we have a simple matrix, a 3 by 3 matrix, and we multiply that by a 3 by 2 matrix. So the output, of course, will be a 3 by 2 matrix from our matrix classes. So this matrix A, as you can see, the values are all ones. And then matrix B, we have a random values here from 0 to 10, between 0 to 10. And as you can see here, if we multiply these two matrices, we get these values. Now, what you observe here is that if you've paid attention to matrix class, you know that this multiplication will be this row multiplied by this column, right? And so on. So this row multiplied by this column will give us this value 14 here, as you can see. So if you take a keen look at what happened here, you will see that this 14 is basically the sum of these 3 values. That is because our value here are all ones. So it would just basically be the sum. So, and so on. If we do for the second one, it will be the same, and so on. So the 16 value will come from this, multiplying this row. And you can see it's just the sum of these values. And then we get 16. So this is quite good, but it's not that very much efficient. So in order to make it more efficient, there is this, how do you call it? There's this method in Touch called trill. So as you can see here, what it does is, because we want to predict, we want to prevent the tokens from talking to their future tokens. So we only want them to talk to their past tokens, that is the previous tokens. So there's this method in PyTorch called trill, which will truncate the matrix such that we only get the diagonal, we only get values in the diagonal, in the lower part of the diagonal. So what that means is that all the upper part of the diagonal of the matrix will be zeros. So for example here, all these values are zeros. So these are all the upper parts of it. And then the lower part will only be the part with values here. So this can help us prevent the tokens from talking to the future tokens, as you can see here. So stage 1, stage 2, and stage 3, and so on. So if we do a multiplication of this and this, as you can see here, we will be able to get a similar result as the previous one, but this time the values will not necessarily be the same. So there will be changes in the values in an incremental fashion, as you can see here. So this, what it does, it actually helps reduce the loss in our attention layer, which is very important. The main goal of the training process is to actually reduce loss. So that is the probability of predicting the next token. There should be lower loss or less loss in doing so. And so that was what he was able to do here. So that is just basically simple matrix multiplication. Third version, he introduced a new method to prevent the past tokens from talking to future tokens. So it's called mask field. So what this method is basically doing, it's saying for all the elements where trill is equals to 0, that is, for example, the upper parts of the diagonal here, after we've done trill on the tensor. So we want to replace those 0 values with negative infinity. And so what this basically gives us, if we want to see it in action, so we say WA, and then we can see here, for example, all the zeros in the upper part of the diagonal are now negative infinity. And then next, if we applied softmax to these values, softmax, what it basically does, it's a normalization function. So what it does is it takes the exponential of all these values and then give the average sum of them at each point. So for example, this one will be 1. The average of this, exponential average of this will be 1. And then this one will be basically 0. And so if we try to print that, we'll get these values, as you can see here. So softmax just normalizes the matrix in order to get the actual values. And then next we get the output here by taking this weighted sum, and then we dot that and we multiply that by the input x. So then next, now since, as we remembered, expo 1 must be equal to expo 3, which is the third version of this. So if they are equal, then it must return true. So that's why we're able to get true here. So which means this method, this version also works well. So in version 4 of the self-attention mechanism, we see where he implemented a data-dependent self-attention for a single head attention layer. So what does it mean by a single head? So we only have one head, and the size of that is 16, setting that size to 16. So as we saw previously, the problem with version 3 is that we are always setting the weighted sum values. We are starting from zeros. So all of the values in the matrix will be set to zeros. And if we want the tokens to actually talk to each other in a more efficient way, we don't need to set the entire matrix to 0 every time. So instead, what self-attention does, if we look at the paper here, scale dot product attention. So what it does basically is, instead of setting all those tensors to zeros, we're actually making use of what are we looking for and what do we have. So for example, the key here is what do we have for a particular node, and then the query here is what are we looking for, and then the value here will be the output of that. So for example, so if we take the dot product of the keys and then of the queries, we will be able to get a more suitable weighted aggregated values. Way will now be a data dependent vector. So instead of it just being all zeros, but in doing so, for example, our keys are in the dimension b by t by 16 because our head size is 16, and our queries also is the same, b by t by 16. But we cannot do the dot product of these two because we will get, it's not very efficient. So what we have to do is take a transposition of the keys, for example. So what we want to do, we want to transpose these two values. So we want to set 16 to take t's place, and then t will take 16. So when we do that, we get this matrix. So that's the only way we will be able to get b by t, which is a more data dependent matrix. So we can start from here, and then we can apply our trail as before. And then after that, we apply our weighted mask and then soft mask. And then this will be able to give us the values of way. So that is basically what it does. So as you can see here, our values of way will be the same as before. But this method is way more efficient as it actually follows the paper. So wherein we have queries, key, and values. And then we take the soft marks of the output of that. And then these are some notes that he gave, which I believe you can read. I've actually taken some of those notes and I've mentioned them. Yeah. So apart from self-attention, there's also another method called cross-attention, which was applied in the architecture here. So at this point here, this is where the cross-attention works. So the values from our encoder will meet up with the decoder at this cross-attention layer. So this is where we have our cross-attention layer. But for our nanoGPT, we are only implementing a decoder transformer, so which means we don't need this layer. So we only have our attention layer here, and then we have our feed-forward here, linear and then softmax applied to that. So the last thing to note in our self-attention mechanism, for example, in the attention is all you need paper, we can see they are multiplying the aggregated weight by 1 divided by the square root of dk, where dk is actually the head size. So they are multiplying the output of the dot product of the queries and the keys by 1 divided by the square root of dk. So why are they doing this? So the reason behind this is to control the variance of weight. So the initialization of the weight values, they should be equally distributed in order to prevent overfitting. So this value here, for example, without multiplying it by 1 divided by square root of dk, we will actually get the tensor to be almost the same or more than the size of more than that of our head size, which will cause overfitting. So what this value does, what this multiplication does, is basically it controls the variance. It causes the weight to converge so that the variance value will converge to, let's say, a particular increment that you did on it. So for example, if we run this again, we can see here, I need to run this one again. So if we run this again, we can see here that way will converge to 1. So this will be our variance. Why is our variance very important? If we look at our softmax here, way is being passed directly into softmax. And in order to maintain some control over the distribution of way, we will need to have some variance, that is by what amount does the increment take place. So that's the reason behind multiplying it by 1 divided by the square root of the head size. So basically, that's the reason behind that. So yeah, so that's all for attention layer. I believe those are the most important. That is the most important part of this video. So let's take a keen look at the complete nanoGPT code here. So as I mentioned before previously, what we are doing here is basically just predicting the next token or the next character here. So what I observed initially was that when we train this transformer on, let's say, a Chinese text, as I did previously, we basically got a very, very much sensible output. very quickly with just a few number of iterations here, as you can see. So we have like 5,000 iterations, and I was able to get something that actually makes sense. But if we do that for, let's say, with English, it takes much more effort for that. So let's say we change our input here. I have the Shakespeare's text, so let's just change that to input there. And then if we try to run this again, when I try, because it will take some time, so when I try to run it, as you can see, this was the output for that. So this was the output. It barely made sense. So as you can see here, into wood, blah, 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 blah. So, but the pattern is actually good because it's mimicking the original text. So if we look at our original text here, so you can see some similarities with the pattern, just that maybe there's not a single line that actually makes sense. Yeah. So basically that's it. So we'll stop here. And if you want to go into more detail on how this self-attention is made, so we can see where he created a multi-headed self-attention layer here, this one, because according to the paper here, we have multiple attentions here that are coupled together. So basically that's what he did here. So we have this multiple headed attentions. So this basically what it does, you don't have to specify your head size and your number of heads, sorry. You can basically set that as a variable, and then you can put that value as a hyperparameter when training your model. So that is what it does. So as you can see, if we look at the paper here, what is happening here is this is our multi-headed attention, and we are passing the projection here, the linear layer, and then there is a dropout. So this is also another important part. So what does dropout actually do? If we look at the dropout paper, so what it does, it just prevents the neural network from overfitting. So these values is actually usually in various key parts of the transformer. So it's in the feed-forward layer, and it's also in the, let me see, yeah, it's in the feed-forward layer, and it's also in the multi-head attention layer. So that's what dropout does. It just prevents the layer from overfitting, the network from overfitting. And then, yeah, and then we have our forward pass, as you can see here. Our forward pass. Now he introduced one simple feed forward layer here, which is this one. So these components, this is what it is. So inside of it, we just basically have a simple layer that is the number of embeddings multiplied and number of embeddings by 4 multiplied by the number of embeddings. So since our network here is, I think it's 16, yeah, so 32, sorry, so it will be 4 by that, and then that will give us 32 head size. So yeah, and you can see he's also applying dropout there as well. And then if we look at the main block of our transformer here, this is the main block, that is this entire thing here. So we can see we have multi-head attention, this one, and then we have our feed-forward layer, which is here, somewhere around there. And then we have basically our layer normalization, that is this one. So what layer normalization does, it's basically just normalizes our output. So from multi-head, after we've applied feed forward, so the output of those will be normalized here. Yeah. And then as you recall from our bigram model, which is just a basic model that actually helps us predict the next token. So it's also, let's say, the brain of the prediction algorithm. And then inside of it, that's where we have our generation function, our generate function, which just generate these text as we see them there. yeah, I believe that's all for today. If you want to, I would recommend actually you go through the papers and then try to take a look at the video as well and see how best you can, let's say, implement a simple GPT from this. So I have done that previously with Dummy GPT. I think it's on my repo there where I post all my practice code for GPT. So there is a dummy GPT that I implemented there, and what it does, it just mimics, as you can see here, it just tries to predict the next token. So for example, this is our data set, and then we're trying to predict what comes after this word, let's say dog, and so on. Yeah, so this one works a bit, it's not that complex, it's a bit simple, so you can start from there as well, but it has all the basic ingredient of what the transformer has. Okay, we stop here for today. See you in the next one. Thank you.